Good morning.
Hi, good morning.
Let's see. I got some new people here that I don't know, like Alyssa. Alyssa, tell me about you. Where are you from? As far as what classes? How did you end up in this class? I'm used to kind of seeing people that took Calc 1, 2, and 1 and 2 for me, and then here you are. So just want to make sure you guys are all lined up.
Okay, so hi, my name's Alyssa Finley. I got transferred from Mary Middleton's
Got
class.
outstanding. You got kicked out. Yeah, we had to cancel that one. Awesome. That's you too, Raymond.
Yeah, I was in Mary Middleton's, and there's only like 4 or 5 people that signed up. So
Yeah, that makes sense. I don't know why I forgot that, but I did. Is that you too, Thomas?
What?
Cody Thomas is in. Yeah, okay, sweet. Oh, I got two Thomases. And Aaliyah, when did you have calculus 1 and 2?
Back in 2014, 2015. So this will be fun.
Oh, it'll all just be like riding a bike. No problem.
Yeah, once we start, oops, I learned for classic now. Once we started doing it in statics, it was like, oh, okay, I kind of remember this.
Yeah, I used to know that. Let's see. What am I doing over here? Let's get rid of that. Awesome. Well, if you are new, my name is Doug Gardner, and I'm excited to show you this awesome world of Calc 3. And for those of you jumping over from Mary, the book is exactly the same, but we are using, and actually this is something I want to show you, Aaliyah. Aaliyah, do you have this book from 2000?
I actually do. I only have the second edition, though. I was wondering what the differences would be.
I think you'll be fine. I do, if I remember right, that they've changed a number of things, but I think all the materials in there. The main thing is to have the book that says early transcendentals in it, not single variable, because single variable only takes you through Calc 1 and Calc 2. And so early transcendentals is Calc 3 and Calc 4. And so let me pull up the syllabus calculus. I think I'll just email you all this syllabus. So you can get into Blackboard, and I already have the syllabus posted in there because that's kind of the only access you have, but I might email you the syllabus right now. Let's see. I can't remember. It's been so long. How did you guys get the link? Did I send you the link to this class via, or did you find it in
I think it's on Blackboard.
Blackboard? Is how you
I
found
think
it?
I got it on Blackboard.
Got it. So the main difference for those of you coming over to Mary is you guys were using Pearson as a product, and we're using MyOpenMath, which is free. So this, in a sense, we're experimenting with a little bit cheaper class. So it isn't going to cost you guys anything, but it's a little bit of a pain for you to have to kind of switch systems. So ASAP, like even while I am rambling here, you might want to consider going into myopenmath.com and becoming a student in there, which gets kind of immediately approved. And then I can't remember which of these things you need to enter. Let's blow this up a bit. I'm pretty sure it's the course ID and the enrollment key. I don't think you need the course name. I can't remember which ones it asked for, but all of your homework is going to be kind of inside that system. And let's see what it. So anyway, syllabus kind of tells you how to get a hold of me. So the one thing I do want to say right off, as far as as far as getting lost and so forth, is I'm working at my computer a lot, and I'm gonna the people in this class that I already had last time, I gave you guys my cell phone number just so you can text me ideally, because I'm more likely to get it right away. And if I'm just sitting at my desk and you've got a 10-minute question or whatever, fire me off a text, and then we can pop into this Zoom, which is kind of my office hour Zoom, and talk for a few minutes and then get back off. And if I'm out and about somewhere and I say, hey, it's 5 o'clock work tonight or whatever, this is a small enough class that I think we can arrange that pretty much on the fly. So rather than picking an office hour and saying I'll be here at this time, because that doesn't always work for everybody, I'd rather you just fire me off a text and we'll see where we go from there. So with respect to the book, my syllabus is pretty clear about what we're covering each day and what chapters. And so my only concern for you, for instance, Aaliyah, with an older book is these chapter numbers like 10.4 might not match yours, because I do remember they moved that around a lot. I think all the material is in there, but I put the title of it on there too. So for instance, 10.6 is alternating series. There's probably a section in your book that's alternating series. But it might not be 10.6. So take a look at that. Anyway, this is pretty well lined out about all the things we're going to cover. And the only other thing I want to show you quickly is just my open math. For those of you that are new to it. There you are. So I'll switch to the student view. So I'll switch to instructor view for a second. I'm working on the problem sets kind of, so you're not going to see them all, but there's a chapter 10, chapter 11, chapter 12, 13, 14. I mean, essentially that's what we're covering in the new book. But I'm only going to kind of, right now, those are hidden just because I want to play with the problem sets ahead of time, make sure I like the problems. Because what we're trying to do basically is switch over to MyOpenMath so we can make this stuff cheaper. So you can just round up in the future students can just round up this book as a physical copy book and nothing else, which is pretty easy to find and very inexpensive instead of $200 or whatever. And then this online homework platform is awesome. It's not a knockoff. It's better than Pearson, in my opinion. Then we could kind of get access to all that stuff for free. So the main thing you're going to be interacting with here is just keeping an eye on the calendar so you don't miss homework. As my syllabus points out, for those of you that are new, almost all my homework is due Sunday night. So for instance, this week, 5, 6, 7, 8, we're talking about stuff. And whatever we get done talking about will all be due Sunday night. I would not recommend, if you have the time, unless you're working or something, I would not recommend waiting till Sunday night to do it. I'd recommend doing it the night we talk about it, because obviously the next day is maybe going to depend on what you just learned. It also gives you plenty of time to ask questions and bother me about stuff until you get it figured out. But the syllabus is in here, and one of the things we're going to be studying in here is something called the convergence test. I got a sheet in there about that that's in your book. Every day after class, I'm going to post everything I write. So I would highly recommend that you not write too much. Anything I'm writing, and I'll be pulling this up in a minute. I'm going to post for you, and I'm also going to post the lectures so you can watch them, watch something later that you weren't clear on, or maybe you missed a day or whatever. And so we can keep you caught up like that. So those will start filling up. and then you're just going to bust in and start doing the homework. Fortunately for you, tonight today we're doing one thing that was kind of left over from previous calc. And so really 10.1, the syllabus is gone, but 10.1 is tomorrow. So that's going to be the introduction to that. But we're going to talk about, kind of introduce the class really this time. So today there isn't even a homework assignment, which I know you're disappointed in. Let's see. So Riley, are you also coming over from Mary's class? Riley Crook?
Yeah, yes, I am.
Cool. So what questions do you have of me as far as logistics? Is there anything I haven't talked to you about that you want to know, or you feel like you kind of understand what you're getting yourself into here?
Yeah, it's looking pretty clear.
Okay. All right. If you something occurs to you, just let me know. For those of you that are kind of new to me as a teacher, the only thing I would say is I very much, I will say, err on the side of teaching for conceptual understanding. I'm not interested in just you getting the problems right in the assignment. I want to qualify that by saying I consider that to be part of my job. I'm trying to do questions that are, similar to what's in your assignment, so you're not totally lost. But I want you to understand the concepts, because I think that's the only thing that's really going to stick with you. So awesome. And then, as always, I know it's early in the morning and so forth, but I certainly appreciate any of you willing to show up face to face. You don't have to. I'm not going to make that a rule, but I gauge whether or not you're making sense of things by what I see. I mean, I know it's a little different for you, your experience of this class, because you're just seeing a white screen right now and not very much of the class full of people. But I do consider this ultimately a human exercise. I don't think of myself as a math teacher. I think of myself as an Alyssa and a Cheyenne and a Ben and a Thomas teacher. Like, I'm teaching you guys, and you have a life, and you have feelings and thoughts, and and math is the subject matter. But this is very human, and you're going to have frustrations over things, and I want to have conversation about those things. I want that to be as close to a bit of a friendship as we can possibly get. So anyway, ramble. So what we're really talking about today is 8.9, and this is what I was talking about. Everything I'm writing here, you're going to have. So you might write a few things down, but I'd rather you be with me, present, rather than feverishly writing, asking me questions, and I'm usually looking down at my screen when I'm writing and so forth. So rather than raise your hand and be polite, I'd rather you actually just interrupt, even though that might feel a little bit rude, because your question is, right now, not 5 minutes from now when I pause. And so interrupt and ask what I want to think. So 8.9 is talking about what mathematicians call improper integrals, which of course is kind of a goofy name. Improper integrals. You already know how to take an integral from last term. But what's an improper integral? Well, let's consider something kind of cool. Let's consider, as our first example, something called Gabriel's horn. An allusion to the angel Gabriel, I suppose. And here's the interesting thing about this. So it's just simply this equation right here, 1 over x, which you're relatively familiar with. And we're only going to look at this thing from x is 1 to x is infinity. And that infinity is where the improper part of this comes from. You're used to taking integrals from 1 to 3 or 2 to 6 or whatever. So let's just remind ourselves, if you decided you wanted to know the area under the curve 1 over x, and you went from, I don't know, say 1 to 4. That's a proper integral. 1 to 4, not 1 to infinity, as we'll do in a second. You might remember from last term, this was one of the tricky ones. What's the integral of 1 over x? I won't ask you, Aaliyah, because you probably don't remember. Feels like a month.
Log of x.
Yeah, that is the natural log of x. Remember, that's actually x to the negative 1 power. And with an integral, you add 1 to the exponent. And so if this was x to the negative 1 and you tried to add 1 to that, all of a sudden you get x to the 0 and it sort of breaks. And it's like, that's a hint that that's the one exception to this. It doesn't work very good. So you end up with the natural log of x. And make sure you're, I don't know, getting in the swing of just writing things correctly. Like I just took the integral's gone. There's no integral sign in that answer. And I still have yet to evaluate this from 4 to 1. And if I do that, natural log of 4 minus natural log of 1, perhaps you remember the natural log of 1 is 0. So this is actually just the natural log of 4. So the area under that curve, Gabriel's horn, is actually the natural log of 4. Awesome. Let's take a quick look at the graph of this thing. And I don't know about y'all in Mary's class, but I'm sort of big on Desmos because there's all kind of cheat features. Actually, you guys in Mary's class, did you guys spend much time with Desmos as a graph calculator?
She didn't use Desmos a lot, but personally, I use Desmos a ton. I like it a lot.
Okay, that's good to know. Once you understand it a little bit, it's way better than a graphing calculator. Because you got color and you got, anyway, a lot more controls. If you don't know how to do this, this is kind of cool to throw in here. But if I go in here and throw a bracket on this and say, I want this thing only to exist where x is greater than or equal to 0, like so. Bam. Now I'm only looking at the right half of this. And I'm only concerned about, well, actually, let's even make this even more interesting because really we wanted x to be greater than 1. So why do you think somebody gave this kind of the, I don't know, religious designation of Gabriel's horn? Why would somebody call it that, do you think? Why would you say that's the horn?
Because there's probably no end to it. It's probably infinitely long.
Yeah. If you let that thing go to infinity, does it make sense it's actually laying down against the x-axis, but it never actually gets there? So it's infinitely long. It's not like an ordinary horn. So I don't know, maybe that has something to do with it. So, all right, that's cool. And of course, you can go in here and either type or go into functions and find integral. For my class, you're of course reviewing all of this from last term, and I say, awesome, let's go find the integral, the area under that curve. This is one of the places that Excel really shines. What happened? Throw in a parenthesis. There we go. And I love the fact that, I don't know why, but notice it isn't answering that question yet, and that's because it doesn't like it if you don't write things correctly. So notice its cheat button is a little easier to use than your graphing calculator. And I'm fine, by the way, with using Desmos on a test. And so apparently that's the logarithm of 4. I'm not going to bust out my calculator and check, but you should while we're sitting here rambling. And so that's the area from 1 to 4. But an improper integral is where we don't go from 1 to 4, but where we go from 1 to infinity. And I wonder what, unfortunately, it's very hard to copy on this. Undo. Actually, I never have figured out how to copy. This is an app. This is an app on my iPad as opposed to the computer version. So I'd love to be able to copy that, but it seems like there's no way to do so. Awesome. So what's your thoughts? What do you think the area under that curve is going to be if we go from 1 to infinity, an improper integral?
I predict 2.
You said 2, Vale?
Yeah.
I'd say that's a pretty reasonable guess. If I take it out to 40, though, notice it went beyond 2. So I actually agreed with you, Vale. I thought that was a really good guess. In the end, this is what this class is studying. Now that would seem like why would you want to do this? Or, why would you ever want to take an integral? That's the only jump between what you just did in this class, at least one of the most interesting parts of this class, is where one of the limits of integration now goes to infinity. And so, now what? Well, if you get way out here at 40, and notice I can't tell what those boxes are worth. Well, yes, I can, because see the little 0.2 there. So notice when you're out at 40, you're still above the x-axis. You're always going to stay above the x-axis. But, how much area are we gaining? What if we keep going out there? Notice it just keeps getting closer and closer and closer. And this is another place Desmos is so much better because, moving around like this, I'm doing it kind of in the way you would do your cell phone. You're just pinching stuff together. Notice how much closer we are out there. So what if we went out to 160, since that's where we are about? What do you think it's going to be out to 160? Or, as I said before, what do you think about infinity now? Like, what if we keep going with this? So if I back up and throw 160 in it, notice it got over 5. So
I put in 1 billion and it's at 20.7.
You put 1 billion in. That's interesting. I wonder what happens. I wonder if there's any way to put the symbol infinity in here. You'd think I'd know the answer to this, but I do not. I wonder if Desmos has a symbol for infinity.
Shouldn't it be OO?
Could be OO, which is I don't think it's going to like that. I don't think it's going to see that as infinity. And one of the important facets of all of this is, I'll try OO, is that infinity is not a number. Does that make sense? I mean, actually, if Desmos allowed you to type infinity this, I'd really be surprised. I like what Cheyenne said. She put 1 billion in there. And, again, you could just start going to type a bunch of 9s in there too, which makes it even larger. Like, I wonder how many lines it'll let me even type. Uh-oh, I got excited and made a fraction out of it. Notice it seems to get up to like 38.58. What'd you say you had, Cheyenne, when you put 1 billion in? 20, you said 20.
Yeah, 20.7.
So notice I don't even know how many 9s because I just kept hitting them. We can't even see the dumb integral anymore. So that's quite a few 9s. But did you notice it wasn't growing when I kept adding 9s? Come on, man, let me back up there. So see how the answer ends in 0836? So I'm adding 9s. Do you see how I added? I just added like 5 9s and it stayed at 0.0836. Isn't that kind of weird? So it sort of appears that it's approaching a limit. Well, 38 point, it looks like we already see it. Does that make sense? So this is an interesting conundrum, I guess you might say. Let's see, I want to bring this over so we can at least have this in our notes. I don't even know what that number is. So when we did the integral from 4 to 1, do you agree from your knowledge of Calc 2? Oh, you idiot. from your knowledge of Calc 2 that you are adding infinitely many, infinitely small rectangles, even from 4 to 1, right? A proper integral.
Yeah, your height is f of x, and then dx is your base.
Yeah. And dx is the width of your rectangles, which is ultimately 0. I mean, calculus, we let that literally be 0. So even from 4 to 1, you have infinitely many, infinitely skinny rectangles to add together, right, to get the area. And thanks to the fact that there were infinitely many, we were able to get the answer to this to be equal to something, which is crazy. Because you literally have infinitely many rectangles, which actually is just an idea. It's not, infinity is not a number. But what we're doing this term is saying, we're even making it worse by saying not only are there infinitely many rectangles, but even how far out they are is infinitely. Like you never stop. You just keep adding rectangles. So I don't know if Desmos was even able to handle that. You know, is that even accurate? Like it said 38.58359 and so forth. Is Desmos really able to let me type in that many nines and that's actually correct? I'm not really sure. I'd be surprised if it was, but would you agree? It looks like it's approaching a limit. Like there really is an answer to it, even though it's infinitely far out there. That should bother you. Because doesn't it, I mean, if you move to the right a little, like you never stop. I mean, that number I put up there with all those nines is a really big number, but it's nothing next to infinity. Do you understand that? How many nines is it if there's infinity of them? Well, we just barely got started. So isn't there more area to go out there? So, you know, could this ever actually have an exact answer if one of our limits of integration is infinity? If we say, what is the area under this curve? Gabriel's horn, what am I doing? What am I doing? What is that really equal to? Well, we could say approximately 38, but it turns out the answer to this is what mathematicians will call, you're probably going to hate this word before we're done now, but this is what mathematicians actually call divergent, which is sort of code for, well, infinity. It turns out that actually never stops. They're 38.58359. As I said, we barely got started. And if we went further, we could get that over 40. Didn't look like it, did it? But if we went further, we could get that over 40. If we went further, we could get over 50. If we went further, we could get it to 1,000. If we went further, we could get it to 50,000. Like there is actually no limit to it. However, there are problems where there is. So this class, actually, at least the start of it, chapter 10 primarily, deals with the difference between something called convergent and divergent. Divergent is where the limit actually never approaches something. In other words, you can't actually say what it is. Remember, this should bother you from last term, even the fact that the area under 1 over x from 4 to 1, the fact that we're saying it's equal, saying it's approximately equal, no problem. You should have no problem for somebody saying, yeah, it's approximately this number. But for us in calculus to say, no, it's actually perfectly equal to the natural log of 4, that is mind-boggling because there's infinitely many rectangles. Infinity is not a number. But there are problems where there actually is an answer to this. Let me give you one of them right now. Really, Gabriel's horn does not become a horn until you start talking about rotating it. What if we rotated it around the x-axis? I'm going to give you a second to think about this. And I asked you for the volume of Gabriel's horn. Remember, it goes forever. And again, we're saying from 1 to infinity, but can you do that? Can you still do that from last term? Again, it feels to me like that was a month ago, but write out the integral for that. You're slicing You're slicing something that really looks like that. And it goes forever, dot, 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 never ends. What's the volume of that horn? Your gut reaction should be infinity to that because it never ends. And so, but the answer is not infinity. There's actually an answer. You're done. Infinitely long, yet it still has a finite volume. Mind-boggling. So from last term, I gave you a second to think about this. That height right there is y. Which is really the radius of your slice. If you make that slice right there, the radius is y. So the volume of your slice would be pi times radius squared times its thickness times its height. But for us, our little slice here, again, I'm just giving you a little head start from last term. That slice's width is a little bit of x, and that height is a little bit of y, is y. So I can replace the height with dx, and I can replace the radius with y. And so now I just have to add those up. So the volume of Gabriel's horn is the integral from 1 to infinity of pi times the radius squared. Notice I'm working with x, and so I'm going to replace the y with what y is equal to in terms of x, 1 over x. Yeah,
Just going to be pi.
Brandon says pi. Notice this integral is not because it's squared. Because it's squared, you really end up with the integral from 1 to 0. The pi could be brought out front if you want, and that really becomes x to the negative 2, which means you can just do regular power rule. You can add 1 to that and then divide by that number. If I add 1 to that x, it becomes negative 1. I divide by negative 1. Now the integral is taken, and I just evaluate this thing at infinity and at 1, and I don't forget that there was a pi out front. So just to make it look a little nicer, isn't that really pi times x to the negative 1 looks weird? So it goes to the bottom as positive 1. And the negative, it's just negative is somewhere. It doesn't really matter where the negative sign is. So really what we're looking at, because remember, infinity is not a number, but we're going to be plugging infinity in this term every time. And so what happens to 1 over x as x gets really large? Mathematicians would say, what's the limit of 1 over x as x goes to infinity? You can't just plug in infinity because infinity is not a number. But what happens to that number? This should feel very easy to you. Like you can explain it to somebody. This isn't magic. What happens to the number 1 over x if you put huge numbers in it for x?
It approaches 0.
It's on its way to 0. And so you can't put infinity in, but you can say the limit of it when x is infinity is 0. So you end up with 0 minus, when you put 1 in for that, you end up with negative 1. So you end up with 0 minus a negative 1, which indeed, as Raymond correctly said, is pi. So you have an infinitely long horn, and yet it has a finite volume. And it's kind of weird that it's pi. And, you can see mathematicians nerding out, because we love the number pi and we're all excited about it. And so here's this horn and it has a volume of pi. I mean, it's just crazy, isn't it? Now notice as a result of spinning it around, we ended up finding, remember, the area under a curve, because notice that Desmos or your calculus skills don't look at this as a volume right here. It's seeing that like as an area under a curve. You understand what I mean by that? In other words, it's still just, it's finding an area, but in this case, the area means a volume because we took pi times radius squared. And to let a little bit of the cat out of the bag, goodbye, you. I want you to take a look at these two next to each other. Let's take 1 divided by not x, but x squared. Choo, choo, choo. Do you see the difference between 1 over x and 1 over x squared? Here's what it comes down to in this class, and we'll hit this a little more formally a little bit later on. But basically 1 over x approaches the x-axis so slowly that you never get an answer. It just keeps getting bigger and bigger and bigger. But the green one approaches way more quickly. Do you see that happening? In other words, think about when x is like 5. Well, the red one is 1 over 5, 0.2. But the green one is 1 over 5 squared, 1 over 25, 0.04. Like the green one is approaching the graph, approaching the x-axis so much faster that it actually approaches, you get a finite answer, not an infinite answer. So the area under the red graph, infinity. The area under the green graph, not infinity. The area into that green graph is actually 1. From 1 out there forever is 1. And then we multiplied it by pi as a part of our problem. That's just weird, isn't it?
But the green graph never touches 0. Right?
Exactly.
So how does it?
That should bother you, right? Like the green graph never touches. So how could you go forever? If you go forever, aren't you still continuing to add more and more and more? So that should bother you.
Yeah, it's bothering me.
Good, good. That means you understand it. If that's not bothering you, then you don't understand this. It should bother you immensely that the area under the red graph is infinity and the area under the green graph is 1. Is 1, perfectly 1. What do you mean? There's no way. Again, let's just play with that for a second. If I say, what is the area under the green graph from 1 to, let's start with a few 9s up there. G of x, bam, bam, bam. Dx, bam. So it, not surprisingly, is close to 1, but it hasn't made it to 1 yet, right? Again, I'm actually curious to see what Desmos is going to do with this. Come on, let me up there. Thank you. So I'm slowly adding 9s. Boom, boom. Notice it says undefined all of a sudden. Actually, I had no idea it was going to do that. Why is that? Why do you think it is? Why did it suddenly go to undefined?
Because you must have passed where it crossed the x-axis.
Well, it never does, though. This graph never crosses the x-axis. Because if you think about 1 over x squared, if you put 5,000 in, 1 over 5,000 squared is still a tiny positive number. So it's never going to turn negative. And 1 over x squared, no matter how big of a number you pick for x, is never equal to 0. And it would have to be equal to 0 to land on the x-axis. So I'm just guessing that, it's like, it blew its mind. Like I'm surprised a little bit because it didn't seem to have any trouble when I had like 59s out there a second ago. But basically the answer in the area under the green curve is 1. It's not approximately 1. It's not approaching. Well, I guess you could say it's approaching 1. It's exactly correct. Now, this isn't that new to you. Like we did this last term too, when we said, what's the area under this curve from 4 to 1? And we said there's infinitely many rectangles. Well, you can't have infinitely many rectangles. And yet we eventually got to the place where we said, no, the area is perfectly the natural log of 4. But you probably just forgot. That should still bother you. What do you mean you have infinitely many rectangles and yet you're saying there's an exact answer? Remember, if there's infinitely many rectangles, how wide are they? There's 0. That's how wide they are. They can't be infinitely many unless their width is 0. And if their width is 0, then all of a sudden, like, wait, what happened? What just happened then? Because infinitely many, infinitely skinny rectangles means there's infinitely many heights, but their widths are all 0. And so who's going to win? It's infinity times 0 here. So this is what this class is about. This is the conundrum. The area under the green curve converges to 1. The answer is 1. Converge is the word you're going to get sick of before we're done here. The area under the red curve diverges. Not cool. Not cool at all. Mind blowing. And then secondly, like, who cares? Like, why would somebody do this? Is this just mathematicians gone wild, so to speak? Like, what, is there any purpose in this? Breathtakingly cool purpose coming our way a little bit later. It's amazing some of the things that result from this that are useful. This, what I just showed you, is the reason you have a graphing calculator, for instance, that will tell you the natural log of things and so forth. So we'll talk about that. Let's get rid of a few of these 9, so at least it produces an answer. Throw it in the notes. Now, while I'm throwing this in the notes, what I'd like you to do now is answer the question, what is the surface area of Gabriel's horn going from 1 to infinity? What's the surface area? Can you still pull off the surface area formula? My guess is, oh no, foggy, I can't remember.
Well, you need the arc length formula, right? Which is root 1 minus f prime of x squared.
Yeah, 1 plus. 1 plus.
Right.
The square root of 1 plus f prime of x squared. Nice job, Vale. I'll pull it up in a second too, so. So again, rather than racing past this, like, oh, you already know this, this is just a good opportunity to see whether you can kind of pull this back or reason it out for yourself. This is why I teach the way I do. If your understanding of this was memorization, then you probably have already forgotten it. If you have it now, you will have it in 2 months. But if you can reason this out a little bit for yourself, if you can draw pictures and kind of get it back, as I'm about to do, so we're talking about rotating this horn, and we come out to some location right here, and we make a slice of this thing, but this time we're concerned with the surface area of that slice. And so its radius is still y, but surface area is 2 times pi times radius because that's the circumference of that little belt, that little slice out there, times its height. That's the circumference of a cylinder. That's the surface area of the outer part of a cylinder. It doesn't look like a times. So what is that for us? Well, our radius is y. Our radius is a y value. And that height, this is what Vail just reminded us of, because that height there is a bit as an angle, it's kind of a hypotenuse, if you will, not a horizontal line. Because it's a hypotenuse, it's not just dx. It's the Pythagorean theorem with dx and dy. Whoa, that was drunken looking. If this is dx and this is dy, if you do Pythagorean theorem with dx and dy, you get the square root of dx squared plus dy squared, which we niftily rewrote last term. I'm not going to remake this, but we niftily, is niftily a word, rewrote that as 1 plus dy dx squared, or f prime of x squared. That's what the height is. So my surface area then would be from infinity to 1, 2 times pi times the radius, which is y, except for we're working with x's, so we're going to switch it out for x, times the derivative. What's the derivative? If f of x equals 1 over x, let's see, what would the derivative of that be? 1 over x is the same as x to the negative 1. Derivatives say take the 1, multiply it out front, so that would become negative. Negative, and then you subtract 1 from the exponent. So now that negative 1 would go to negative 2. So it's negative 1 over x squared. But then that's squared. So I guess we could say then, if we pulled the 2 pi out front, since I'm squaring a negative, I guess that'd be 1 over x to the 4th, wouldn't it?
Shouldn't that be negative 2 over x squared?
No, because then you're mixing up derivatives and integrals, because taking a
Oh, wait,
derivative,
yeah.
you first multiply the exponent out front, and then you decrease the exponent by 1. Thank you for interrupting, Vail, and for asking our question immediately.
Yeah, sorry, I forgot the order of operations there.
Well, it's hard because we went backwards all last term. And so, what's the answer to that question going to be? Well, would you agree that this statement is going to be a bigger number than this statement? Would you agree with that?
Yes.
And since this diverged, in other words, it went off to infinity all by itself, then certainly this is going to also go off to infinity too. In other words, if the smaller answer 1 over x went to infinity, then an answer that's slightly bigger than that is going to as well. Now again, that demands some proof, so to speak. So far, I've just kind of told you that it did. We saw 1 over x going to like 38.5, and so you're just, I'm asking you right now just to believe me that that actually goes to infinity.
So wait, we've got a horn with a finite volume, but infinite surface area, and
That's
what?
exactly right. So you can see why someone said, man, let's give this like an angel's name or something. Like, this is crazy. We have a horn of infinite length here. and it has a finite volume, yet an infinite surface area. That's just kind of mind-boggling. It's just kind of cool to think about. It might feel a little less surprising that it's infinite surface area, because if this horn just kept getting skinnier out there, way out there someplace, it's kind of just so skinny, it's teeny, it doesn't have much volume. But if even like a wire, if it got so skinny it was like a wire, isn't there still, like, you have to paint it, don't you? I mean, the surface area is painting something. So the fact that it goes way out there, its volume is going to zero. But if there's anything there, if there's a human hair way out there, that's how small it is way out there. It's like, well, it's still, still got to paint around the outside of that thing. Maybe that's helpful. But yeah, this is very troubling. Good observation, Dale. Wow, crazy. Well, let's just play with one thing really quick here. I mean, we're saying the answer to that is infinity. Well, what if you evaluated that? We just did this a second ago, and we had the natural log of x, and now we got to evaluate it at infinity and 1. And so isn't that equal to the natural log of infinity minus the natural log of 1? But the natural log of 1 is just 0. So the question is, what's the natural log of infinity? Do you agree with that? I mean,
Well, that's like asking what e to the power of what equals infinity, and there's no answer to that.
nice job. Now, again, you technically can't say the natural log of infinity. Mathematicians freak out about things like this. I don't think they should. I think they should take a chill pill. Of course, infinity is not a number. It's just what happens to this. Well, the problem is that a natural log of a continuously bigger and bigger and bigger number just gets bigger and bigger. Now, it gets bigger really slowly. If you take the natural log of a gigantic number like 9,999,999,999, it's still only like 13.2. It's really, get your graphing calculator out and try it. Like, you can put some huge numbers in there for the natural log. And as Vale said, if you understand your E work, if we said, what is this curious creature, the natural log of junk? Well, let's say it's equal to some number n. Well, doesn't that mean the same thing then as e to the n equals infinity? In other words, what do you raise e to the power of to get infinity? The answer is infinity, like you infinitely many. And as I said, if you don't choose this number over here to be infinity, but you throw in quite a few 9s, do you understand that n doesn't have to be very big to get the answer to e to that number to be a really huge number? I'm just guessing at 12. It's not even close, I'm sure. But it's not like those two numbers are equal. That's what I'm saying.
But they're the same type of infinity, right? Because they're both counting infinities.
Yeah, that's exactly right. And this did lead mathematicians to wonder if there's sort of like different infinities somehow. Because then in the end, n is like a slow infinity, so to speak. Like, it's going to take forever to get there via n. But in a sense, that's a proof, a sort of a proof at the fact that the area under the 1/x curve is actually infinity. It's infinite. And again, instead of saying it's infinite, mathematicians call it, as I summarized back up here, they call it divergent. It doesn't approach something. So it's kind of a mind-boggling idea, isn't it? It just kind of hurts your brain a little bit.
I think it's weird that they were sooner to decide that there were different infinities rather than just deciding that infinity is a destination that can be reached slower or faster.
Uh-huh. It's very true. So really, in your book, section 8.9 is actually asking you to evaluate some integrals like this. And so if we'd have had time, we would have actually covered 8.9 as a precursor to this class. And you weren't introduced to any of these ideas. But as an example, if we were doing an assignment in 8.9, kind of the 8.9 assignment type of questions, let's just see if you can actually evaluate these yourself. What about this? What if I went from infinity to 0 and I asked you to evaluate the integral 1 over e to the x dx? This is convergent. It actually has an answer, a numerical answer. Can you get it? Just going to give you a second to play with it.
Is it going to be 1?
Let's see. And again, the cool thing about Desmos, your graphing calculator, is you can at least check your work. You can't type infinity in, but you can put a pretty big number in up there and at least verify that. Some of you right now are thinking the integral of that is the natural log of e to the x. That's not true. The only integral that's natural log is 1 over x, not 1 over anything else, not 1 over x squared, not 1 over sine of x. See this as e to the negative x. The integral of e to the junk is e to the junk. That's the curious thing about e. Its derivative and its integral are itself. But chain rule says you're not done. If you want to be technical about this, you make a substitution and let u be equal to negative x. U will be equal to negative x, because I'd really like it just to be e to the x, not e to the negative x. And that would mean that du is equal to negative dx. Oh, so the only thing I have to change is a negative sign. And so the integral of e to the negative x is negative e to the negative x, which is really just negative 1 over e to the x. It's a little easier to think of it like that when you go start putting infinity and 0 into this. So what happens to that when you put infinity in? If you put a huge number in for x, what happens to that?
It gets small really fast.
It gets
Small and
small.
negative really, really fast.
Really fast. It's negative 1 over infinity really fast. So it's on its way to 0. And then minus, what happens when you put 0 in for x? E to the 0 is just 1. And so you have minus negative 1 over 1, which is negative 1. And so, yeah, your initial answer, Raymond, was right. So this actually converges to something. Again, it's just crazy. It is 1. It's not approximately 1. It's 1. So we're not only adding infinitely many rectangles here, we're even adding an infinite length of infinitely many skinny rectangles now. It's like 2 infinities contributing to this craziness. So these are improper integrals where infinity is involved. What about this one? What about infinity to 5? And I'm picking this to make your life easy because this is a cube root. And if I go from infinity to 5, that makes your life a little easier. What would you say the area under that curve is?
Divergent.
Vale immediately says divergent. See what you think. I'm going to go graph this while you're thinking about it. Kind of looks like, at least from 5 to infinity, looks kind of like Gabriel's horn again. So so wherever you are in that, take a look up here for a second. If I took Gabriel's horn 1 over x and I slid it over into the same position, because I took this graph and slid it right 4. If I do the same thing with Gabriel's horn and slide it right 4, what do you notice about those two graphs to the right of 5? We said the red graph diverged and had no exact answer because the area under that red graph did not approach the x-axis fast enough. Well, notice the black graph is even worse. Based on this graph, the answer should be divergent. It should be that it's even worse. Give you another second to think about that. The question is, does the math kind of bear that out? Did you find yourself getting infinity for an answer this time instead of a nice answer like 1? So it approaches the x-axis even slower than 1 over x did. So I can already tell by looking at this that it's going to be divergent, but let's do the math. Well, wouldn't this be from infinity to 5 of x minus 4 to the negative 1/3 power? Isn't that the easiest way to take the integral of this? And then there's a 6 that just kind of comes along for the ride. And in the interest of time, I won't make a substitution here. I might let u be x minus 4. But if I did, du would be equal to dx. And so since that's just an x, not a 2x, really the integral of that junk is, well, add 1 to the exponent. If I add 1 to negative 1/3, I get 2/3. So it's now x minus 4 to the 2/3 power. I added 1 to it. And then I divide by 2/3, which is really multiplying by 3/2. 6 times 3/2 would be 18/2 or 9. And now I'm going to evaluate that at infinity and at 5. Remember, 2/3 means squared cube rooted. So if I take infinity, if you will, and put it inside here, infinity minus 4 is still infinity, but if you take infinity and raise it to the 2/3 power, isn't it still going to be infinity? I mean, you are hindering it, if you will. on its sprint to large numbers, because you're saying you're going to take the cube root of it and square it. So you're making it get there slower, but it's still going to go to infinity. So again, we would say this thing diverges. So it doesn't have an answer. It approached 0 too slowly.
So is the cutoff point for the exponent of whether or not it's divergent or not, is it a -1? Or is it some nebulous constant that we have to work out?
Yeah, notice we've investigated 1 over x. We've investigated 1 over x squared. That's not where squared goes. 1 over x, or 1 over x to the first, 1 over x squared. And now we really investigated 1 over x to the 1/3, didn't we? And 1 over x to the first diverged, 1 over x to the 1/3 diverged, 1 over to the x squared, though, actually approached it fast enough that it actually converged to something. And so you're onto something there, Bale. There is a line, like where's the line between something that converges and doesn't converge? It turns out that the 1 over x is it. That's the line, but we'll talk more about that later. Let me give you one more question. And it actually pertains to this. What do you think is going to happen if we considered 1 over x to the 1.1 power? Let's do that now. Switch colors. What did I just do? C. So this might be our last example. We'll see. What about from infinity to 1, not of 1 over x, but what over 1 over x to the 1.1? Barely over 1. This is a very important idea along the lines of what Vale just asked. Like, where's the line? And of course, I assume you are immediately recognizing, hey, that's x to the -1.1. Just want you to think about what happens to that integral thanks to the 0.1.
Yeah, the equation just ends up infinity minus 10.
Close, not infinity. You're on it.
Well, 10x to the 0.1 minus 10. All right.
Yeah, so don't you add 1 to that exponent, which when you add 1 makes it x to the -0.1, right? And then you divide by that -0.1. Just the power rule. Add 1 to the exponent. And I could write that a little more cleanly by saying, let's see, negative, that's really -10. On the bottom, that's 1/10. So I could, dividing by 1/10 is multiplying by 10. And then this moves to the bottom as x to the 0.1 power. So what happens when you evaluate that at infinity and 1? What happens when you put in a large number? What do you get when you put infinity in? You get -10 over what?
That thing still goes to 0. It's still -10 over infinity.
Yeah, would you agree the 0.1 hinders infinity's approach to infinity, but it's still going to get there. If you take the 10th root of it, that hinders it. That's chopping it off a little bit. It's making it crawl instead of run, but it's still going to get there. This is going to be -10 over infinity still, minus, what happens when you put 1 in? 1 to the 0.1 power is still 1. So this is going to go to 0. And so you end up with minus a negative 10. This converges to 10. This has a finite answer. It's 10. The area under that curve is 10. And so for that reason, that's kind of the line. And this is one of our tests. So we're gonna have tests for convergence that will drive you crazy. But this is one of them. If you have an integral where the x on the bottom is raised to a power more than 1, even slightly more like this one, 1.1, even 1.01 would have converged to something. I think 1.01 would have been 100 or something like that. I'm not sure. I gotta think about that. So this one actually converged, this one converged, this one diverged, and this one diverged even worse. And so this one really is the line, as it turns out. If that exponent in the bottom is more than 1, then it actually will converge to something, even though there's an infinite length to this. It's just kind of a crazy idea. I think this last example is a good one because you can see it happening, if you will. You can see, I think, negative 10 over infinity to the 0.1 power. You can see that that's going to get to 0. So the 0.1 hinders infinity's approach to infinity. It's still going to get there. Crazy idea. I've got a few more examples, but I don't think I'll do them since I'm not giving you an assignment about this. But I do want to leave you with one other thing. This is really, this is not new. This is something you've done before. If I take the decimal 0.29, except for, let's not just have 1 9 there. Let's not just have 2 9s. Let's have infinitely many 9s. The question is, does that make it to 0.3? Maybe I'll even make it easier. I'll get rid of the 2.
Yes, yes, it does.
Does that make it to 1? Is that equal to 1? Is it less than 1? You're certainly not going to say it's greater than 1.
The proof that I'm aware of is just subtract 1 from both sides. And then you have to somehow say that after 0.000 an infinite number of times, you have some difference between 1 and 0.999 repeating. It's, yeah. That's a proof
I'll show you a simple kind of proof for this, and again, but what this is really getting at is infinity. Like we're all day today, and since we started this calculus this year, we've been talking about and touching infinity, and very few people are not going to answer this question with a less than sign until they take some calculus, because it just feels like, you know, go as long as you want, have as many 9s as you want, it can't ever make it to 1. Does that make sense? Your common sense should still agree with what I just wrote. Your common sense should agree. But the problem is, that's because you're thinking of infinity as a number. Infinity is not a number. When do you stop adding 9s? You never do. And of course, you know, your brain can't do that. We have to stop adding 9s once we get tired enough. But we're literally saying you never stop. How many 9s are there? There's infinitely many of them. So here's one proof of it. So it's kind of a neat algebraic proof. If you say that this is equal to some number n, you could think, okay, I have this equation now, and I'm sort of hunting for, you know, what is this equal to? Certainly it approaches 1, but you know, is it equal to 1? I'm hunting for this number. Well, because it's an equation, would you agree you could multiply both sides by 10? And so that's still true. But the key thing about infinity is, did I just lose one of my 9s down here? Since by multiplying by 10, one of my 9s popped over on the other side. Are there any less 9s here than there were before? The answer is no, because of infinity, because infinity never stops. Infinity is not a number. If you did stop, then yeah, you have 1 less 9. But if you don't stop, you have no less 9s than you had before. So now that you have 2 equations, what if you subtracted in this direction? Like I took 10n minus n, then isn't that 9n? And if I subtract it over here, 9.9 repeating minus 0.9 repeating is 9. So I just solved those 2 equations to unknowns. And now if I divide both sides by 9, I get n is 1. So that's an algebraic. There's nothing wrong. It's not a trick. It is 1. That makes it to 1. It is not less than 1. It is equal to 1. And so the example I gave earlier, like 0.29 repeating, is also equal to 0.3. 0.3, not 3. It makes it to 3. So this business is not, I guess what I'm saying is, it's not new. This is something we've been playing with for quite some time. But what we struggle with is we can't get our mind around infinity. Infinity means you don't ever get to quit, ever. And saying something silly like, I'll just add 1 9 every second for my entire life. Every second I'll add a 9, and that's all I do to exist as a human being. And then when I die, my kid will take over. And when he dies, his kid will take over. And so on and so forth. Like, that's still not enough 9s. You never get to stop. So that's the hard part. So the big takeaway from this is kind of has to do with how quickly does your curve approach the x-axis. If it approaches quickly enough, then it will converge to something. Let's take a quick look, since I have a second here. I don't think I'll post this in the notes, but let's just take a look at these different examples. I'll just type them a little faster. So we had 1 over x, we had 1 over x squared, 1 divided by x squared, red, the same exact color. And we had 1 over x to the 1/3 x raised to the 1/3 power. And we had y equals 1 divided by x raised to the 1.1 power. Struggling, let's go with orange. So do you see how those are all approaching the x-axis at different speeds? The yellow graph is approaching quickly enough that it actually has a finite area under it. The green graph is approaching just barely quick enough that it has a finite area, but the red graph is the first graph that approached just a hair too slow.
Wow.
Looking at it this way kind of makes you realize why the integral of the green graph is greater than the integral of the yellow graph.
Mm-hmm. That's exactly right. And even if I did something like this, y equals 1 divided by x raised to,
Doug, not quite.
well, equals 1 divided by x raised to the 1.01 power. Notice that's so small you can't distinguish it from the green. Let's see, is that right? The green and the purple. Yeah, basically the red and the purple graph now are so close you can't see them unless I zoom in. So the purple graph will actually converge to something. Again, what you'll end up with is not infinity to the 0.1 power, you'll end up with infinity to the 0.01 power. And although that will hinder infinity's approach to infinity, it's not going to keep it from getting there. And so that's just kind of interesting. So the purple graph will actually converge to something. And I don't have to stop there. I could add more zeros. Dunk, dunk. Now they really look the same, right? Yet, if I get closer, dunk, 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 dunk. Oh, a little bit lower. Purple graph will converge to something. The red graph will not. The red graph is the line. It's just kind of crazy. How's your brain? Is it smoking?
Yeah, it's crazy to think about because they're like so close. It's like there's a difference of one's infinity, one's not infinity.
As a side note too, one of the things that fascinates me about this is, our ability to play with this and look at it and so forth is so advanced compared to the people that invented this stuff. Like they couldn't even graph things like this. They didn't have graphing calculators and even graph paper, even pencils.
Oh man, how
couldn't
did they
graph things
do
like
it?
this. It's just amazing. What'd you say, Ren?
Just how did they do it? That's crazy.
Well, they were a lot more into proof than you and I would be naturally. I'm not a true mathematician. I'm convincible a lot more quickly than a mathematician. So for a mathematician to prove, because what you really have to prove is that the natural log of infinity goes to infinity, and that isn't as obvious. And so they would prove those things. And but it is kind of funny when you think back to integrals. The integral of 1 over x, that was the only one that was natural log. All the rest of them, you just add 1 to the exponent, and you're able to do it kind of in another way. And so it was like this weird exception. What's the integral of 1 over x? Well, instead of using the power rule, you had this weird exception of natural log. And so it's kind of cool that the line here was defined by like almost a totally different function. Natural log came into play, and so it's just interesting. Anyway, that's enough for now. So what we're going to start with tomorrow is sequences and series, and start kind of building some of the structure beneath this. And in the end, I'm going to show you a whole bunch of infinite series. You probably have never spent any time with series before, but anyway, we're going to build a foundation, and then we're going to start. I'm going to show you how you can actually replace the sine function with a polynomial, and how you can replace e to the x with a polynomial. Anyway, that's too nebulous for me to describe right now, but we will take off from there. As always, stay after if you want to talk about anything further. Otherwise, I'll see you in the morning today.
Sweet, thank you.
Bye.
So why don't we do chapter 9?
That's a good question. Let me look and see what that is. Chapter 9. I think it's just the time thing. Chapter 9 is just a brief introduction to a class I'm teaching this summer. It's differential equations is an entire class. And so it's really just because of time and the fact that we'll tackle it more deeply in the summertime. But it sure is a neat concept. Whew, I hope you're in some spot where you can take it. It's really beautiful.
Would you recommend looking at it a little bit if you're planning on taking that class?
No, you don't need to, because in a sense, I'm gonna teach chapter 9 to you along with everything that follows it. So I'll be showing it to you.
Gotcha.
I'd say it'd be a shame not to look at it if you aren't going to take it this summer, but That's a good question.
Alrighty, later.
See y'all.
I actually had a question about that very first 1 over x function.
Yeah, sure.
So once we took the integral of that, we were just doing the natural log of 99999 minus the natural log of 1, right?
Yep, that's right.
So on Desmos, if I use the predefined integral tool, it gives me undefined when I have 10 nines in there. But when I do the natural log of 10 nines minus the natural log of 1, it gives me 23. And then when I do it on my calculator, I think I got a slightly different answer. It was,
Yeah, and keep in mind what you're doing when you take a natural log. The best way to think about natural log is there's no such thing. It's undoing an exponent, kind of like when I say, what's the square root of a number? There's no such thing. What you're doing is you're finding a number that when squared is that number. And so in a sense, what your machine, you're using different machines to try to achieve the same answer. Your machine is trying to find out e raised to what power will give you 9999999. Well, e itself is an irrational number whose decimal goes on forever without any kind of a pattern. And so, when you get your graphing calculator out, as I'm doing right now, and ask it to tell you, and you say, hey, I'd like to know what E is. And so you go second E, and it says, there it is. But it's like, nobody knows what E is. Don't forget that. It has infinitely many numbers, and there are nerds in the contest to this very day to try to figure out how, it's out to, billions of decimal places now that people have figured it out. Same with pi. But nobody actually knows what it is. And so, the calculator gives you this approximation here, but it's not perfect. And so every machine, based on, whoever made it, is basically playing around with how accurate do they want to work. And so, yeah, you're going to get totally different answers to that. So,
yeah, that makes sense.
but you're exactly right. It's really kind of weird when you just throw a whole bunch of nines in there and say you take the natural log. It's amazing how much reduces that number. I mean, what is that, 999 billion? And you take the natural log, and now it's down to 25. Like, wow, that is a really, that's an example of how slowly it grows if you're having this number that wants to grow really fast, and then you decide to hinder it by taking the square root of it or something like that. Well, when you take the natural log of it, and we're going to talk about this in a couple of days, but you're hindering it the most you could possibly hinder it without making it come to a stop, like it won't get there. So
Okay.
that's really the main thing. Yeah, that's a wonderful question.
Okay. Thank you.